Welcome back, everybody, and I hope you had a great weekend. So the topic this week, I changed a little bit things with respect to what we did last week because I wanted to cover some of the statistical analysis, which we also will need for the exercises this week and for the project itself. Now, one of the nice things with some of these simple models is that we do actually have a pretty straightforward way to perform a good statistical analysis. I know that many of you may not have had a coherent course in statistics. So that means that there may be elements which you're not too familiar with. This is actually something which is very unfortunate with many bachelor programs, that statistics in a way has fallen out from many programs as a course by itself. And then the kind of idea has been that you put in some element here and some element there, but then you never get the kind of coherent picture of actually what it means. So hopefully some of these concepts, you may have seen them. Another thing which I did was actually to make a video of what we call the second order moments, which are named in terms of algorithms like ADA-grad, root mean square propagation, and ADAM, which you're going to encode in the project. Now, these methods, and let me just quickly point to where you can find them. These are also methods which we will discuss during the lab sessions this week and next week. So the second moment of the gradient, that leads to these popular methods. And if you remember back, so this is a short repetition from last week. If you look back at what we did last week, we discussed stochastic gradient descent with and without what we call momentum, which I like to call just a memory, where you keep track of the results from the previous iterations. That is a way to update the so-called parameters or the coordinates, which they often also called. But then we don't have a proper information about the Hessian matrix, which is the second derivative of the cost function, which we are optimizing. So we are searching for the roots of the gradient. That means we want the gradient to be equal to 0. And then when we implement Newton's algorithm, we have to evaluate this Hessian matrix, which we don't want to do. In particular, if we have millions of parameters, as you will see when you move into deep learning methods, then clearly this is something which we would like to avoid. And we replace that with a learning rate. And as you saw from last time, to find the proper learning rate is actually, and to get it right, is something which becomes a kind of art. And the kind of standard recipe is to set up a grid of learning rates and simply let the calculations run with all these learning rates, and then you pick the best fit. That's the kind of standard approach. That means you run many numerical experiments. Now, these methods, which we did not discuss last week, but which you find in the video, and I invite you to take a look at it, the algorithms and code examples are all included in the lectures here. And the kind of way to do this is actually to avoid that eta is too large or too small, which means that you will have a very slow convergence or no convergence at all. If it's too large, you may actually have strong oscillations. And as we saw last week, you may even get results which become not a number, but just increasingly large numbers. So this is the kind of situation we have to live with when we run machine learning codes. Now, these methods, which we also discussed in the video, like ADA-grad, root mean square propagation, and ADAM, are methods which try to compensate for that in a kind of cheaper way, where you actually calculate the gradients squared, and you only keep the diagonal elements of something which is proportional to the diagonal elements of the Hessian matrix. And so the motivation here is to use, instead of having a global one, which we did in the exercises last week, and we tuned it so we got a good result, is actually to try to now have an adaptive learning rate. And this is especially useful for sparse features, where you actually relatively rarely active features accumulate little gradient, so their learning rate remains comparatively high, ensuring that they're not neglected. And you also have active features which accumulate large gradient sums, and then their learning rates automatically decreases, preventing too large updates. And the algorithms which we discussed in the video are algorithms like AdaGrad. And in the codes which you find below here from the last week, you will then find examples of the implementation of these algorithms. So AdaGrad is a method which works extremely well if you have nice convex functions. It converges pretty fast. But still, you would start with a fixed learning rate. So you cannot escape running experiments with a grid of learning rates. So you could start with 10 to the minus 1, then you run a new calculation where you start with 10 to the minus 2, 10 to the minus 3, etc. And then you pick the best possible result. And in this particular case, what we are doing now is to do an element-wise multiplication of the gradients. We accumulate this, so that means that the denominator here becomes larger and larger. And that means that the learning rate becomes smaller and smaller. So you start with the initial one, this epsilon, and then you have an element-wise multiplication with a gradient. And this is what you update. Now, the other method, which is called root mean square propagation, there's a discussion here of different methods, there are pros and cons, is actually then performing an update with momentum. This is essentially the difference between AdaGrad and root mean square propagation. And according to legend, it was proposed by Jeff Hinton, who got the Nobel Prize in Physics last year, for instance, having presented what are called Boltzmann machines, a very popular deep learning method. And this method here is also pretty easy to implement. So you have the same update of this number R, which accumulates gradients, but now you keep an information with a parameter rho, which then keeps track of the information from previous steps. And essentially the update algorithm, the parameter theta, is pretty similar to the one you had for AdaGrad, except that now you have a momentum part. Now, Adam updates both the denominator and the numerator. So it includes the best of root mean square propagation plus a further momentum update. And Adam is, if you go through the literature, you will often see that that is the method of choice for updating the learning rate. Now, when you then scroll down the lecture notes from last week, what you will find then, in addition to a discussion of the different methods, is actually below here an implementation of the different methods. And if you first we just repeat with stochastic gradient descent, and then present AdaGrad, which is the one which comes here. This is the one with AdaGrad. And then there is a similar one with root mean square propagation. And in all cases, we use stochastic gradient descent. Now, for the project examples, which we have, as we mentioned last time, the stochastic gradient descent, in particular when we have just a one-dimensional function, which we fit with a polynomial, you will often see that stochastic gradient descent most likely gives results which are not as accurate as the standard gradient descent. In particular, in these cases which we are looking at, just to get the codes up and have them functioning, you will be pretty, how to say, you may even be disappointed. Why do we do stochastic gradient descent? Now, the problem kicks in when we are dealing with tons of parameters, like in neural networks, and we don't know whether this is a nice, smooth, convex function, or whether it's a pretty rough surface we want to find the minimum in. Okay, so take a look at these codes and also take a look at the video. It's not that long. And what I wanted to do now is more to go into the statistical analysis, because we are going to discuss methods which are quite important when we deal with machine learning. And the methods which we are going to look at, after we've looked at statistical interpretation, is something which is called resampling techniques. And then in the exercises in week 36, you try to reproduce, no, week 35, you try to reproduce this figure 211 in the textbook by Hasty. Now we are going to make a better analysis of what happens when the mean squared error, for instance, for the test data starts to differ largely from the one from the training set. And we are going to discuss the equation for the bias-variance trade-off, and that's a kind of holy grail when you're discussing the quality of your model. We also have, since we are dealing with normally a few data points, then we use resampling techniques, which are ways to improve the amount of data points without actually running a new experiment. Now, in our case, you will see that for project one, the function is pretty simple and we can regenerate the data without barely noticing that the computer has generated new data sets. But when you have a real data set, most likely it's very unlikely that you will get more data points. Essentially because many experiments are very expensive, they can be dangerous to repeat. There are many conditions which makes it impossible to get new data. So these resampling methods, one of them which you will encounter today is called bootstrap. Many of these methods have funny names like bootstrap, jackknife, blocking methods. The bootstrap is widely popular when you have a small data sets. And there's another method which is called the CV, what's the name called again? Cross-validation. Thanks. So these are the methods which we will discuss in more detail today. We will also discuss them a little bit during the lab sessions and parts of next week. And then you should have most of the material which is needed for project one. Any questions? Okay, so what I'm going to do now is to jump over to the whiteboard. But before we do that, I would typically recommend some of these videos which you have here. There is a website called StatQuest by Josh Starmer. I don't know if you had time. Anyone had time to look at these videos? They're pretty fun, actually fun. And they're extremely good. So take a look at them because they give you the kind of bird's view on many of these methods. Okay, so let's switch over to the whiteboard after these introductory words. And let's do that one. So we're going to look at some elements of a statistical analysis. And essentially what we will be doing today is to first remind ourselves of expectation values and some of the basic assumptions which we have been doing when we have been setting up the equations for linear regression. So let's look a little bit more in detail of some of the basic assumptions about the data set which we are having. So let's just write this down here, some basic assumptions. So these are assumptions which we make about our data set. So we have some y value, the outcome or the target or the output value. There is a function f of x, which we don't know. And then we assume that there is some kind of stochastic noise. Now, this function here is assumed to be non-stochastic. So if there is a probability distribution which governs y and epsilon, that probability distribution does not affect f of x. So it's easy to think of that in terms of just a plain function like a second order polynomial. But you could also think of this as a function which takes some input when you're running an experiment. So suppose you're running an experiment where you measure the velocities of a car as a function of time. Now, you will assume that time, which you have then as a variable, is not a stochastic variable because you can fix time when you make the measurement. So you simply say at time that we measure that velocity. At that time, we measure that velocity, etc., etc. So it's a general assumption to assume that this function is a non-stochastic function. So the probability distribution, which if there exists one, does not affect f of x. This is going to have important consequences when we are calculating expectation values. Now, this epsilon, on the other hand, is assumed to follow a normal distribution. And this normal distribution has zero mean and some variance, which we haven't specified. So that function, which is something we would label as a p of epsilon, suppose now this is a function of x. This is given in terms of a normal distribution, or it's just a Gaussian, sigma squared, and this is multiplied with the exponential of minus x squared divided by 2 sigma squared. And I guess you've seen this distribution before. So this is a standard normal distribution with zero mean value. Now, the assumption then is that epsilon is a stochastic variable, x is not a stochastic variable, and f is a well-defined continuous function. So we've made some specific assumptions about the data set. And then y, we don't know. So that could have a distribution. And we are going now to look at the expectation value of y. But let's remind ourselves of expectation values. So assume now that we have some variable x. So we have a stochastic variable. And let's just call it x, although it may not be the same as the x which we defined above. Then the expectation value, which is something you will see like that, and this is just a moment of x. This is given by, if you have a continuous distribution, by x over a specific domain. So x is normally a real variable. And then we have d of x, the integral. We have x to the power of n. And then we have a probability distribution, which we use. So this x is now a probability distribution, which x follows, p of x, okay? Have you seen this before? Is everybody familiar with that? So this is a typical definition of an expected value. And if you have a discrete probability distribution, then this x of I it contains now a sum over all the events which you have, and we have x of I multiplied with this p of x and x of I. So this is the case, p is a discrete probability, and you have a discrete set of stochastic variables. Now, the mean value is something which we will define as mu of x, and we are going to write it like this. So this is simply, if we now stick just with a continuous variable, we have a d of x, of p of x, of x. So that's the definition of the mean value. Now, when we are running experiments, our problem is that we don't know the probability distribution. That's a pretty common situation. What we end up doing then is to calculate the sample mean. And that means that, so the sample mean, or the sample expectation value, and that is because we don't know p of x is unknown. And in that case, I'm going to write this quantity as a mu of x with a bar on top of it. And that is simply 1 divided by n of I equal 1 up to n of x of I. And this is normally different from the true mean value. So suppose that you have the true mean value, then you can calculate, you know the probability distribution. then you can actually calculate the mean value. But in general, you don't know the probability distribution, which means that you have to stay with the sample mean value. Now, there is a theorem which is called Bernoulli's law of large numbers, which says that in the limit where n goes to infinity, you are going to approach the true mean value. Have you heard about Bernoulli's law of large numbers? So that's one of these famous laws which you use in statistics. So ideally then, having more and more samples means that we should get a better and better expectation value. Now, the problem which we simply have to face is that the number of samples is often sometime, or quite often, something which we cannot increase, because the data set which we have is the data set which we have. Okay, so these are important quantities. And then we have another quantity, which is the variance. And of this variable x, this is something which I'm going to write like the expectation value of x squared minus mu of x squared. And if we are looking at the continuous distribution, this is now a p of x of d of x, and then I have x minus mu of x squared. So that's a definition of the variance. And this simply measures the spread from the mean value of the different events which we have. And then we square it, which means that squaring the spread means that we will put quite some emphasis on outliers. So in a certain sense, it mimics what we have seen before with the mean squared error. Now, there is another quantity which is also useful to look at, and that is obviously the sample variance. And the sample variance for this variable x is something which I will define with a bar on top of it, and sometimes I will drop it just for simplicity. And this is a sum from I equal 1 up to n. And then I have my event xi minus mu x. But now we are using the sample mean value and not the true mean value. And this is in general, unless n is extremely large, this is in general not equal to the true one if we are able to calculate the true one. Okay. Any questions so far? I assume that these are things which you have seen a little bit here and there. So how many of you have taken one of the basic bachelor courses in statistics and stochastical analysis? You see, okay, it's a good fraction of you. So it means that you've seen these quantities before, right? Now, there's another quantity which we will come back to a little bit later, which is actually very interesting for us. So if you now look at your design matrix, so think back to that one, the design matrix. We can write this out as a set of column vectors. So if we look at that one, if we now think of each column, so this could be the intercept column, and putting vector signs here in order to distinguish that from, so this should be an uppercase X, so that's the design matrix. Now I can calculate the covariance between two of these vectors. So the covariance, this measures the degree of correlations between the data set in column I and the data set in column J. So the covariance is actually defined for, let's say, a vector xi and xj. This is defined as 1 over n. And we sum from I equal 1 up to n. And then I have my xij minus, and then I have my mu of xj, so that's the mean value of that specific column vector. And then I have my xi, so this is actually a sum over L. So this is going to be, let me just, I actually did this, so this should be an L here. So there's an L of I minus mu of xi I. So this is actually the definition of that quantity. And what you will see then is that you can write this, since these are vectors, you can write what we are going to call C of X. So every one of these is just a number. So what you have here ends up being a number. And it measures the degree of correlations between the data sets in each column. So if they are uncorrelated, then the covariance is exactly equal to 0. Now, you can rewrite this in terms of 1 over n, and this is actually your design matrix X transpose times X. This is actually very interesting, because this is the quantity we use to invert in ordinary least squares. So the covariance matrix, irrespective of whether we are doing a ordinary least squares or ridge or lasso regression, is actually given by this matrix, which also by accident is the second derivative of ordinary least squares mean squared error. So there are some interesting things which we will pick up a little bit later. We are going to leave this now, but I just wanted to mention it, because this has important consequences when we are going to discuss a method which is called principal component analysis. So this is just a small aside, but you will encounter this a little bit later in the course. And one thing, just to sneak in a reminder of what we have done, you may remember that the eigen from the SVD analysis, that the eigenvectors V of I from the SVD decomposed matrix is then given by the singular value squared times V of I. And V of I are then the orthogonal vectors of the matrix V in the singular value decomposition, where we have a V0, V1, up to Vp minus 1. Now, diagonalizing the correlation matrix, as we will see later, gives us the variance. So I'm just leaving this now because what I wanted to do is to discuss a little bit more in detail some specific expectation values. So let's go back. So this was a small aside, which will be a little bit interesting later. Now, what we have done till now is to assume that y tilde, our model, is given by this design matrix times the parameters theta. And this is in principle going to approximate this function f of x. Okay? This is what we have been doing till now. Now, what happens then is that since this function f of x is a non-stochastic variable, then the basic assumption we are going to do is that x times theta is also a non-stochastic quantity. So I'm going to introduce a kind of shorthand notation now. So what we have, if we now look at y of I, that is going to be given by the sum over j equals 0 up to p minus 1. I have the component x of I, and then I multiply with theta of j of theta j. And then I have some noise, epsilon I here, okay? This is the model which we have made, the basic assumption we have made about the data, okay? So I'm going to introduce a shorthand now, where when you see this x of I and this asterisk sign, this is going to represent the product of the vectors theta with a specific row element in that matrix X. So this is just a shorthand which I'm setting up because I don't want to bring in these summations of a sigma all the time, right? So this is just a kind of shorthand. and you will see that in some textbooks. It's just meant to avoid the kind of clutter you get if you want to include everything. Now, let us then ask the question, what is the expectation value of y of I? So in principle, I should now be able, if somebody gives me a probability distribution, I should be able to calculate the expectation value of one of the y's. So that's the mean value of y. So this one, it should be equal to the expectation value of xi, and then we have this asterisk sign, plus the expectation value or the mean value of epsilon of I. Now, if you look at the last term, what is the expectation value of that one? If you look back at the assumption we are making about the data, yeah, that's 0, because we have defined epsilon to be given by a normal distribution, which means that we put the mean value equal to 0. So this is something we can put immediately equal to 0. By definition. Now, what we are interested in is the probability of y. So this, what does P of y look like? Now, one thing which we are going to assume, obviously, so if you look at this expectation value, which you have here, so this is a probability we are looking after. So when I take this expectation value with that specific probability, what that is going to mean, so if we take this quantity here, this one, and we break it down into a standard probability calculation of theta, this is in principle going to be given by an integral over the y values. And then I have this probability which acts only on y. And then I have these x's which then, since they do not depend on y, are independent of y. Now, these probabilities, so this is also multiplied with d of y, these probabilities are normalized. So we assume that they are normalized in the domain we are looking at. So since this quantity here is just a constant in terms of y, it does not depend, it's not a stochastic variable, that means that we can just pull it out. And that means that in this case here, we're just left with this integral, which is 1, multiplied with these non-stochastic variables. So we are looking after the probability which governs y. So if you have that probability, you can generate new y values. In general, we don't know this probability. So what we are going to do then is now simply to set up the expectation value, because we have E of y, I, and that is simply going to be given by this x of I multiplied with these vectors, which is the same as the sum over j equals 0, p minus 1, and we have assumed that these quantities are not stochastic variables. And then epsilon of I has mean value equal to 0. So in principle then, we can actually write E of y is now simply given by x times theta. Now, in this case here, what we can assume is, since epsilon is given by a normal distribution, we now make an assumption about y. And this is the assumption which Gauss made when he derived the ordinary least squares equation based on a probabilistic assumption. So let's now take and make an assumption. So the assumption which we are going to make is that this y follows a normal distribution. So y of I follows now a normal distribution where we have a 1 divided by some 2 of pi of sigma squared. And then we have the exponential here. And in this specific case, we have y of I minus xi theta. This is squared, and it's divided by 2 sigma squared. So this is something which we would write as a normal distribution with x of I multiplied with the theta values. And then it has a variance, which we are going to come back to. So I'm going to come back to this one. I haven't showed you that this is the variance of y. So let me show you the calculation of the variance after we have used that model here, okay? So later we are going to show, and this is actually one of the exercises this week as well, is that the variance of y. So we're going to show that the variance of y of I is actually given by this number sigma squared. So we have a mean value, which is given by this quantity here. And then we have a variance, which is given by this one. Then we make the assumption that y follows a normal distribution, but with a mean value, which is not 0 anymore. So what does that mean? Can we actually derive the ordinary least squares equation from such an expression? This is something which Gauss did back in the 1850s, I think. So the question now is, let's assume that y follows that distribution. Can we derive the ordinary least squares equation using this probability for y? And then we are going to use a probability where we have y of I with a given x and given parameter theta. So this bar means that what is the probability of y given theta? And in this particular case, this probability distribution is now given by 1 over 2 pi squared sigma. And then we have the exponential. And then we have minus, and then we have y of I minus xi times theta divided by 2 sigma squared, like that one. So we are going to call this one simply P of I, okay? Now, what I'm going to make I'm going to make an assumption now. And you have probably seen this acronym before, IID. Does that ring a bell? Independent and identically distributed events. So we are going to make an assumption about the probability for all the y values, which is simply the product of the probability of every single y value. So the assumption which we make now is that there is a y, and this is a vector now, and then we have the design matrix of theta, which is simply the probability from I equals 0 up to n minus 1 of this P of I. And in the right-hand side, I'm suppressing the variable theta and x and y. And this is given by this Gaussian distribution. Now, this is called a maximum likelihood estimation when we are going to find the parameters theta. So one thing we have assumed is that y's, the yi's here, they are identical and independent, identically distributed, the D for distributed, and I for independent, and the other one for identically distributed. So every y follows the same distribution. And then we make an ansatz that the total probability, since these are independent of each other, that there are no correlations between the different y values. That is one of the, yeah. What?
When the y values are different means.
What they mean actually. So the y value is your
like average different mean.
Yeah. So they what that means? Yeah.
So like the y values,
yeah.
Wouldn't they have different means, so they wouldn't be identical?
Or because the y values will be different. So all the y values are different.
Yeah, so the distribution would be the same because the average is different, so they wouldn't be identically distributed.
They are identically distributed because they follow the same distribution. So every y follows a normal or a Gaussian distribution.
Yeah, but wouldn't you have to specify the average and
Oh yeah, but the average is something which we already have calculated for every y of I. So for every y of I, we calculated the average here. So this is for the total y's. And then for each individual one, it's given by that specific component in your design matrix times theta. So instead of having 0, which you had for epsilons, you now have a distribution which contains this mean value. So every single y of I is now given by this distribution here. So that means that I can generate a new y value using a Gaussian distribution. This is actually one of the big things with generative methods, which you are used to through ChatGPT, but also when you ask ChatGPT to make a figure of a horse for you, because that has been trained with generative methods to reproduce horses. And then when you ask it to draw a new horse with 5 legs, it can do that for you. It will look like a horse with 5 legs then. But then it uses a probability which has been trained on the data. So normally what we have done till now is to train a function. But you could equally well train a probability distribution. The assumption when they are identically distributed is that all the y's simply follow this distribution here with a given value of theta. So we can then draw and make new y values from this distribution here. Now, what we want to do then, when you look at this distribution, is to optimize the value theta so that we get the maximum distribution. So the theta now is something which is obtained by maximizing this distribution for all the values of theta of this P. So this becomes our cost function. Now, if you look at this function, this is actually not so nice to calculate the derivatives of, because we are going to calculate the gradient of that function. Is there a smarter way to actually look at this maximization problem? Anyone who have encountered that? You can actually rewrite this maximization problem in terms of a concave function. Alternatively, you can put a minus sign in front of it and you have a convex function. So suppose that is my cost function, the probability. So what I want now is to find the maximum theta, or the theta which maximizes the probability. Nobody is looking after a theta which minimizes the probability, right? So because if it minimizes, you have 0 probability. So when you're training parameters, you want to maximize the probability. So what we are going to do then, if we now follow what we have done before, is actually to calculate the derivatives here, the gradients of y, of x, given a theta. And we want to have that to 0. But you see then that we have a product of probabilities, which means that the derivatives are going to look pretty ugly. Can I circumvent that one? There are some nice simple functions which allow us to simplify it and still have a concave function if you maximize, or take the logarithm. And you remember the logarithm? If you have a minus sign in front of the log, that is a convex function. If you have a plus sign, it's a concave function. So what you can do now, if you prefer minimization instead of maximization, you can optimize. Instead of this function, you can then just optimize. You define a new cost function, which is simply minus log. And then we can minimize, because this is a strict convex function. We mentioned that 2 weeks ago when we looked at the properties of specific convex functions. So we will simply take then the log of this guy here, y, and then we have the x's and theta. So if I do that, let me just quickly do this and then we take a break. So if we do that, what I get then is now simply a sum. So this is simply minus, and then I'm going to get if I take the log of the product, this is simply going to be a sum from I equals 0 to n minus 1. And then I have the log of the individual guys, y of I, of x, of theta. And if you go back, so let's just do that one because we can do that quickly. If I take the log of an exponential, then I'm simply left with the argument here. I have a minus here. There's a minus log, so that becomes a plus. And then I have a minus in front of this one, which is just a constant. So this one, which you see here, is just going to be equal to a constant, which will now have a minus sign here, minus n half of log of 2 pi sigma squared. It's actually a plus here because we have the square root, inverse square root. And then I have plus, and what I will have in the sum here is I equals 0 to n minus 1. And then I'm going to have y of I minus this x of I, theta squared, divided by 2 sigma squared. And you've seen that before. So if I now take the derivative of this function, of d theta, of c of theta, and drive that one to 0, you see then that this parameter here is independent of the theta. So the derivative of that one is something we can just throw away before we do any calculation. Then this sigma squared is just a constant, which we can multiply away. So then if I just multiply away this one, what I have here is just the mean squared error, except for a factor 1 over n. See that? It's pretty neat. So if I do that, this is actually going to be equal to n divided by 2 of log of 2 pi sigma. So the cost function, c of theta, and then I have plus, and then I can multiply with n here and have 2 divided by sigma squared. And then it's simply, let me just leave out the n here, of 1, and then I have y minus x theta, and this is the norm 2 squared. And when I take the derivative of this quantity of d theta equal to 0, that is going to give me theta equal to x transpose times x inverse times x transpose times y. So I can derive the same equations which we started with in the semester, where we started with plain linear algebra without thinking of any probabilities. I can now assume that the y's follow a specific probability distribution. And I have calculated the mean value. So if I let the y's follow a Gaussian distribution with a mean value, which is x, the design matrix times theta, and a variance, which is sigma squared, then I derive the same equations, which I did with standard linear algebra methods, which we started with. So this is one of the reasons why we like so much these linear regression cases, because you can catch so many birds with just one stone. And now we have the probabilistic or the probability approach to deriving the same equations. This is something which we next week will discuss in connection with Lass and Ridge, So Lassen Ridge is something we introduced in terms of an optimization problem, but we can give an equally interesting statistical or probabilistic approach to lasso and ridge regression. But that's something we will discuss next week. So after the break, we are going to move into the bias-variance trade-off and also remind you of something which is called the central limit theorem. And then we are going to look at how we can assess from a probabilistic approach whether we are overfitting or not. I went a little bit over time, but you obviously get some time back. So we just meet in 15 minutes, if that's okay. Eh? Here. So we can derive the same type of equations starting with what we call a statistical approach. And then what we have done to achieve that is to calculate the mean value of y. And when we calculate the variance of y, we will find that that is exactly equal to sigma squared. And that is one of the exercises this week as well. So what I want to do now is to remind everybody about the central limit theorem. And when we have looked at the central limit theorem, we are going to introduce a method for resampling, which allows us to generate new data sets. And you will also see that that method, which is called the bootstrap method, follows the central limit theorem. So the bootstrap method is a way to generate new data without actually creating a new data set. And I'm coming back to what the bootstrap method means. And after that one, we are going to look at cross-validation, which is somehow the kind of standard method for trying to obtain a better estimate of the mean squared error when you run many numerical experiments. So I'm going to go back to the Jupyter notebook, and I will remind you about the central limit theorem. So how many here remember the central limit theorem? Yeah, so let me just bring this up here. So what does the central limit theorem says? I mean, there was a hand up here. Yeah? Yeah. And so just to repeat, if you have, let's say, many stochastic events, and each of them are governed by the same probability, and these stochastic events are given by independent and identically distributed stochastic variables, then in the limit of infinitely many, the probability distribution for all these variables is going to approach a Gaussian distribution. Okay? So if you have independent and identically distributed variables, so in the lecture notes, you will find a quick derivation of the central limit theorem. By the way, here you will also find exercises which I invite you to look at, which are relevant for the exercises this week, or the solution to the exercises. But if we now look at, so this is what we discussed, the maximum likelihood estimation. So let's now take a quick look at the central limit theorem. And I'm going to use the slides here because I want to show a demonstration of the central limit theorem using the bootstrap method, which is a resampling technique, which is a way to cheaply generate new data sets with the same data. That sounds like a kind of very strange thing. Now, what we have is a set of stochastic variables where each of them, so you can think of this as the mean values of a given set of experiments. And so we have this n averages, so that means that the mean value is then given by the sum over all the mean values divided by the number of experiments. So all these variables, x's, the x's, have the same distribution. So when we now want to find the limit, when this m goes to infinity, then we can actually ask what is the probability for this z given the small independent probabilities here. So then we are putting a constraint on this set of integrals where we require that the mean value should be the sum of the mean values of all the x's. Now, we can then manipulate that with the delta function by simply using this expression for the delta function. So the mathematics here is a technicality, and it's not that, perhaps not that important, because what we want to discuss is actually bring back the central limit theorem, because the bootstrap method is a simple way to show how you can obey the central limit theorem when you just resample your data points. So the probability distribution, then, we can rewrite this probability distribution in terms of this Kronecker delta, but now we have this to the power of m. And the whole thing is that all these guys here, the p's, which you see, are the same for all the different stochastic variables. So that is what the mathematical expression is the same. So it could be a set of Gaussians, but it could also be a set of what we call Poisson distributions. Any distribution which gives us independent and identically distributed variables. So when we say identically distributed, it's the same mathematical function. The variables can be different, but the mathematical function is the same. So there are some tricks here where you then can show that when you Taylor expand this one, you can actually then recognize terms here. The first one is going to be the mean value, x here, minus the mean value, so that will give us 0. And the second term is actually going to be the variance. So when I calculate this integral, I get 1 minus this variable q times sigma squared divided by 2m. And I can show then that this p of z, in the limit m goes to infinity, that this actually becomes a Gaussian itself, a Gaussian. So the small p's which I had, these ones don't need to be Gaussians, but they have to be independent and identically distributed, the variables x. If that is not the case, then you cannot prove the central limit theorem. So that's a very important assumption which you make about the usage of the central limit theorem. If you break that assumption, that the different probabilities p do not correspond to independent and identically distributed variables, then this is not valid. So if you think of the way we distribute grades, that actually assumes that you guys are basically independent and identically distributed. And then you can actually use a Gaussian distribution as a kind of ansatz for distributing grades. I never like that. And I actually don't follow that Gaussian distribution of grades. Let's see. Yeah. Okay. So when you do that, what you can show is that the new standard deviation is given by the original one for the individual distributions divided by the number of experiments and the square root. And this is the kind of formula which many of you probably have seen before. Does that ring a bell? So this is essentially one of the central results of the central limit theorem. One is that you approach a Gaussian, and the other one is that the sigmas which you see here, which are the standard deviation, the square root of the variance for the individual probabilities, the new standard deviation is actually given by the individual one divided by the total set of experiments. And since you don't know the mean value exactly, you often have a formula where you have n minus 1. So I'm going to skip some of these, but I'm going to say something about the bootstrap method, because now we are going to use that to make a demonstration of the central limit theorem. And when we've done that, we are going to introduce the bias-variance trade-off and how we can use the bootstrap method to numerically see what happens when we now run into regional overfitting. So let me bring up the whiteboard first. And I'm going to present to you the bootstrap method, which is a very popular resampling technique. So, and we do simply these resampling techniques because we often have a limited set of data sets. So resampling with bootstrap. The original paper by Efron was introduced in the 70s, and often, as happens with many of these methods, it was proposed as an ad hoc modification of another very popular method to resample data, which is called the jackknife method. And when it was suggested the first time, it did not have a sound mathematical proof, but then the proofs came a little bit later. So the original paper has 20 or 30,000 citations. So this is one of the very popular methods to generate cheaply new data ensembles. So the bootstrap method starts actually, so we start with a domain of variables, domain, let's just call this for D, and we have a set of variables, C0, C1, up to some C of n minus 1. And then I can calculate the mean value, and I can calculate the variance of this quantity. So I can calculate the mean value, the sample mean, which is just 1 over n, and I sum from I equals 0 to n minus 1, and then I take the Ci values. So this is typically what I would do, and I know that suppose now you have only 1,000 data points. Then most likely your mean value will differ from the true mean value if you were able to calculate the true mean value. So the sample mean does not need to match 100% with the true mean value if you knew the probability distribution. So in principle, this number which you see here is different from the true value, if you know that one. Normally, we don't know that because we don't know the probability. And we can also calculate the variance of these variables Z, which then would simply be 1 over n. So this is the sample variance of n minus 1. And then I have a C of I minus this mu of Z squared. And this, the variance is actually, this quantity here is actually the sample mean variance. And that does not need to be equal to the exact variance. Now, what we can do now is to reshuffle the data. So this is the bootstrap, and it's extremely simple to implement. So reshuffle data randomly. So then I'm going to create a new data set, which I call for D prime. And this will be a Z0 prime, a Z1 prime, up to some Z of I prime, of Zn minus 1 prime. So what I did was to take that data set and I reshuffle it. And then I pick new numbers. The first one I pick, I put into Z0. The next one I put into Z1, etc. But I do this with replacement. So with replacement, that means what could happen then is that this C0 is exactly equal to the original one. But then this C prime, since I do this with replacement, I could actually have the same numbers appearing several times. So this is reshuffling. And then I'm going to mark it here with replacement. So that means that we put back the number which we picked out, and then we pick randomly again, which means that we can actually pick some numbers twice or 3 times or even more times. Then I have a new data set. What you do then is you just repeat this again and again. So if you go back to that discussion we had about the central limit theorem, what we could do then is actually to create new data sets which follow the same distribution as the original C, but the data sets will be different from those which we have. So in a way, we are taking the same numbers, but we're just reshuffling them and pretending that this is a new sequence of numbers. Then, what we will do then is that we repeat this B times. And then the hope is that this mu of B, which is now the sum over all these new samples which we have with B equal 1 up to the final value B of mu of B, well, this is the mean value of each of these new domains, is then closer and closer to the true mean. So hope is that this gets closer to the true mean. Then with that quantity, we can also calculate the variance. So we would have then sigma B squared, which is then given by 1 divided by B. And it's pretty common to have a B minus 1 because these are no longer independent of each other. So you have B1, but I'm just going to leave that out. And then I have my mu of B minus this quantity mu of B, which we calculated here, squared. And this kind of variance is the one you would like to now approach more and more the true value. So in a sense, you're not generating new numbers, but you're just reshuffling the numbers you have. So it's a kind of cheap way. And Efron showed later that this actually approaches the true variance. So we are not going to go through the proofs of that. We're just simply going to state it. You see, this is the algorithm. So let's show how we can implement it, okay? Now, the implementation of that is an example code, which you will see in the lecture notes. So this is a simple implementation of the bootstrap method. So what we are doing now is just to calculate and set up 10,000 points for a Gaussian distribution. And I'm going to have a mean value equal to 100 and a variance equal to 15. So I'm just calling the mean value 100. And you will see now that what I'm doing here is to set up the original mean value and the sigma, and I do 10,000 data points. Now, what I can do then is to do a bootstrap. And in this particular case, I do a bootstrap 10,000 times. So, but I'm taking the same original points and just reshuffle them. And the way you would do that in Python is simply to call the function random, randint, and you take the whole data set, and that will reshuffle all the numbers. So every time I call this one, I generate a new data set by reshuffling. And then I use that data set to calculate the mean values, expectation values, etc. So what you will see now, if I take 15 divided by the square root of 100, which means that if this is working correctly and it follows the central limit theorem, I should actually get something which goes like 15 divided by square root of 100, which is 10. Okay? No, sorry, the number of points is 10,000. I have 10,000. So that should be 15 divided by 100. Sorry. And that means that I should, because I have 10,000 points. So if I do that 10,000 times now, it means that here I should see, instead of 15, I should now see 15 divided by 100, which should be 0.15. So let's just run this. And in this particular case, you will see now that the mean value is basically the same. It should be. This is the original one. There is a reason why I don't get some numbers. So if I were to calculate my Gaussian distribution with 1 million points, then I would get something which is not 99.94, but much closer to 100, because I have more points. So this is just a fourth of the random number generator, which is not truly random. And I'm just calculating the mean value for 10,000 points. So I will not get, with a limited data set, I will not get 100, and I will not get 15. But what you're seeing now is that by resampling this 10,000 times, I'm mimicking the central limit theorem. So I'm getting the original 15 divided by the square root of 10,000, which is 100. And you see now that I'm getting 0.15. Now what happens then, and this is the thing which is interesting for us, when we do that, if I plot the histogram, this is actually much more interesting. So remember now that if you look at the spread here, so you see that this with 10,000 points is getting to be a lookalike of a Gaussian distribution. If I had put 100,000 or 1 million, it would be much, much smoother. And you would also see numbers getting closer to 115. But what I've done here now is actually to run this calculation 10,000 more times. And that means that I'm narrowing down my standard deviation, which means that my standard deviation now, since I am making new points without calling a random number generator, so I would have gotten the same result or similar result if I had called new random numbers 10,000 times. So this is essentially the central limit theorem. But what you see is that this cheap bootstrap technique, instead of me calling a random number generator, which every time sets up new 10,000 points and does it 10,000 times, I'm simply reshuffling the same numbers. And it behaves as it should. Does that make sense? So this is a numerical demonstration of the bootstrap method, which avoids us from calling a random number generator again and again and again, but it reuses the same numbers, reshuffles them. We can pick the same numbers, but we are getting now the same result as the central limit theorem. And Efron actually proved this. So it's a method which works extremely well when you have independent and identically distributed stochastic variables. So what you also see now, so instead of having a spread, which was 15, so that's a standard deviation. So I'm assuming that you remember these kind of confidence intervals with the standard, with a normal distribution. So if you go one standard deviation, that is you cover 66% of all the data around the mean. If you have two standard deviations, you're getting to 90% of that distribution. In the previous case, this had a scatter from 100 plus minus 15. Now, what happens is that we are narrowing it down. So our standard deviation is getting smaller. And that's one of the things we want with these resampling methods. What we want is, in a cheap way, to generate new data sets, which then allows us to shrink the standard deviation. And then we can say with more determination that our results are within this value of 100, but now plus minus 0.15. Instead of the previous one, which was 100 plus minus 15. So if you now look at the standard deviation, the original one was 15. We don't get 15 because we have only 10,000 data points. In that specific case, we are now having a result which has a mean value of 99. And then I can predict 99 point something with 66% confidence if I had plus minus 15. If I do plus minus 2 times 15, then I have roughly 90% confidence. Here, due to me having produced in a cheap way more data, I am shrinking the standard deviation of my expected values. So here I would say that with Bootstrap, I am now confident that I have 99%, 99 something, plus minus 0.15 as my error, one standard deviation. So this is the kind of games you can play around with these methods. So where does that bring us? Why is this interesting? It's interesting because if you now take this Jupyter notebook and you replace 10,000 with 100,000, you will see that this is going to take a lot of time. If you replace 10,000 with 1,000,000, it's going to take even more time to generate the random numbers. So you see quickly that Bootstrap or even the brute force generation of new numbers is quickly going to take time. So often the Bootstrap is a method which is used on smaller data sets. And you will see that quickly here. If I now change 10,000 with 100,000, this is going to use time. And you will see that it's previously, we just got the results immediately, but now it's going to take more time. So I'm going to use 100,000 bootstraps. So which is going to be faster than me generating new 100,000 data sets, but still it's going to take time. So if you have larger data sets, this becomes less efficient. And that's why this method, which is called cross-validation, which we will cover most likely next week, but I've also discussed it during the lab sessions, is actually much more efficient than the Bootstrap. So the Bootstrap is not that much used. And you see it's still running. And now there's obviously a risk, if we wait a little bit more, that you will be exposed to one of my horrible lame jokes. I'm going to refrain from that. So let's just move on a little bit. And we can come back to this one. Because you see quickly now that when I'm doing 100,000 bootstraps, this is going to be time consuming. And the case you're looking at is a one-dimensional case, and it's what we call a baby case. So let's just wait and come back to this. But now we are going to look at the bias-variance trade-off. And I want to show you an example first. And then I'm going to discuss the equations. So what I can do is to rewrite my mean squared value in terms of three quantities. So this is my mean squared error. I can rewrite that one in terms of, if we just scroll down, and then I'm coming back to the derivation. It's also one of the weekly exercises this week. So I hope you can forgive me if I jump back and do the derivation afterwards, because I wanted to show you what is going on here. So I can rewrite my mean squared error in terms of a term which I call the bias, where this is the mean value of the model I'm making. This is my y value. This is actually an approximation because in principle, the exact expression should have f here, the unknown function. And we replace f with y. And this is the variance of the model itself. Now, what is this going to mean? So let me just go back to the Jupyter note, to the whiteboard. And let's see, now it's gone. You see now that we are still not getting exactly 100, and the standard deviation has now been reduced further. So this is divided by the square root of 100,000. If I plot the histogram, you will see something which looks nicer. And you see that it is much more concentrated. So if I do a spread of one standard deviation, this is the value of the mean value, which we had here, which is 99 point something, plus minus 0.0 something. So I'm narrowing down my standard deviation. Now let's go back to the discussion of this bias variance trade-off. So the bootstrap, the way I'm presenting it to you is from an algorithmic point of view. I'm not going through the proofs of the bootstrap method, and that it actually approaches the true mean values and the true standard deviation when you do it many, many times. So it actually, you can show that mathematically. But as you saw, it's a very efficient way to generate new data using the same data set. And it's widely used in calculations where you have from 1,000 up to 10,000 data points in order to narrow down the standard deviation. So you're invoking the central limit theorem. Now, what we want now is the following. So if you go back to this figure by which you had in the textbook, so we have the complexity of the model. And then I plot the mean squared error. And this is for test. Now, one of the things which we will see then is something like this. So this is the red curve. And at a certain point, it starts bending up. So these are the optimal parameters. Now, in the beginning, there's going to be a function here which is going to follow this one. And this is called the bias. So let's just write it down here. So this bias is actually going to be given by 1 over n, the sum over the data points which we have of n minus 1. And then I have my y of I. This is actually an approximation because in the exercise, you will see that you get f of y, but you cannot calculate that one because you don't know it, minus the expectation value of the model. So this will be y tilde. So this is the model. Then, down here, there's going to be a new function which suddenly can raise up here. And this is called the variance of the model. This is the scatter in the predictions of your model. But this is now done on data which was not included in training. So pay attention to that. This is the mean squared error for the test data. So this variance is the variance of the model. So I have y of I tilde, that's the model. So this is the model variance minus this mean value of the model. Oops. And this is squared. Now, let me just rewrite it. Sorry. Let me just give it a little bit more space because this didn't turn out well. So I'm going to put this one on the next page. So this variance of the model is 1 divided by n. There's a sum. So these are the quantity which we end up calculating. So I have yi tilde, my model prediction. So remember that y of I, or y tilde, is x times theta, the optimal parameter. And this is minus e of y tilde squared. Now, let's now look at a data set. And you will find the same data set or example in the lecture notes. So suppose you have a target here. This is your target. this is the one you want to reproduce. So that means that that is this value here. So we want to reproduce that one. And now, suppose now we have these circles. Yeah. So you can think of this as a shooting target, if we want to be a little bit more violent here. Suppose now that the mean value of my data set, this one, is here. And suppose now that my data set, so this is y tilde, the mean value. I do 100 measurements, and the values are scattered all over, like this. So these are the values of y, the individual ones. So these are the y of I tilde. Now, if you look at that, this picture here, and if you now think of the variance, without having run a calculation, what would you expect the variance to be? Large or small? What is the popular vote here? Yeah? Large variance. So the variance here is large. What about the bias? If you now look at the bias, so the bias is measuring the distance between the true value we want to reproduce and the mean value. And that is this quantity. So what about the bias? Is it big or small? It's big. So this is a case of large variance and large bias. And we don't want that, right? That sounds pretty intuitive, right? If we have a model which behaves like that, we will probably be somewhere here. Large bias and large variance. If I give you another example, so let's go back. So this is still the data point, and we have all these circles. And I have a result where my mean value is still here, but all my observations are here. Is that a small or large variance? Yeah, that's small variance. So this is nice. So small variance. But then I guess you would say that the bias is large, right? So this is large bias. So the ideal situation which we want to have, the ideal one, so let me set up that one before we now look at the Jupyter notebook and we end there today. So the ideal situation is actually this one, and then all observations are here. So then we would say that we have a model which has a low variance and low bias. And we can calculate this. So let me just, this is where I'm going to end today, by this numerical example, which you will find in the lecture notes. And then next week, we will discuss in more detail cross-validation. And we will discuss some of these things during the lecture as well. But let me just finalize everything by just sneaking in some more minutes, 1 or 2 minutes. So there is a program example here. Let me just restart it. So you will find the same here, which we discussed now. So this program example is a function which you have seen many, many times. And what I'm going to do now is to take a 500 points and do 100 bootstraps. So I generate 500 points here for X, and I generate my Y, and then I train a polynomial. So this is essentially the exercises you have seen in the previous weeks. It's the same function. What I can do now is to look at the test mean square error, and split that one in bias and variance as a function of the complexity. So in here, I'm now setting up, I'm doing my train test split before anything. I set up a polynomial model, and I say a polynomial of degree 18. So this is the things I played around with this one to get something which looks like this figure in the book here of Hasty. I resample, so this is my bootstrap. I resample X train and Y train, and then I make a prediction. That is my model fit. And I use the test data, and with that, I calculate the mean squared error, the bias, and the variance. And when I plot it, you're going to see something. No, this is the next example, sorry. So in this case, I have 40 points. And what you will see then is something like this. So in the beginning, you have a bias which follows the model. So often when you have a small complexity of the model, I get a bias which follows the mean squared error. My variance is very small. But then at a certain point here, you see now that the mean squared error is increasing. This is the test data. And you see also that the variance is increasing. So this is the region where we are entering overfitting. And if I were to change this data set, in this particular case, I took 40 points and I did 100 bootstraps. So I just regenerated the data again and again. And the reason for that is that I want to have a data set which is, has a little spread in the mean squared error. If I do this now, what you will see is something like that. And that changes the picture totally. In this case, the variance is basically 0. And the bias is just following the standard error, which I have, the mean squared error. So in this particular case, we have a model which basically doesn't overfit. And you see that the mean squared error is getting pretty flat. So everything I do now is to use Bootstrap to narrow down the error or the standard deviation in the predicted mean squared error. Like I did for the simple Gaussian model, where I just shrinked the standard deviation by invoking the central limit theorem. So here again, we are assuming that the events or the numbers are stochastically independent and identically distributed, and that we can use the Bootstrap to generate new data sets without calling a number which sets up a new data set every time. So the Bootstrap is a resampling technique which allows us to avoid collecting new data by simply reshuffling the data which I have. And the hope then is that the error becomes smaller and smaller, and that we can narrow down and say that this mean squared error, which I'm giving you now, has a very small standard deviation. And I trust that this mean squared error is something which is reliable. Then, when you do the bootstrapping, you have a way to at least be confident that your error is decent, or the standard deviation. And then you can play around and study whether you're overfitting or not. So if the variance in the model is very, very large, that's a clear flag that you're overfitting. Okay, I went a little bit over time. I didn't get time to do the cross-validation, which we will discuss in more detail next week. But we will also discuss these topics in the lab sessions this week, but also next week, and obviously in connection with the project. So everything you do now, this kind of analysis, is something which we also want you to do in project number 1. And it's a standard way by which you analyze the quality of your data. Any questions, guys? I know that many of you may have forgotten all the statistics, but I hope this was a quick reminder. And it's a very useful tool to analyze the data which we have. Okay, we see each other at the lab, and enjoy your week, and hopefully the weather gets better.